In Chapter 3.5, Rational Functions, our objectives are to apply notation describing infinite behavior of a function, identify vertical asymptotes, identify horizontal asymptotes, identify slant asymptotes, and graph rational functions. We're also going to use rational functions in applications. Our first objective is to define a rational function and behavior. Let p of x and q of x be a polynomial where q of x is not equal to 0. A function, a rational function, is defined by f of x, p of x over q of x. An example of a rational function is the following for g of x. G of x is equal to 2x divided by x squared minus 2x minus 1. In rational functions, the denominator cannot be 0. We're going to have the following notation of behavior of a function. As x approaches c, a point on the line, going from the right, but not equal c, we say that x approaches c from the right. X approaching c from the negative side, or from the left, we will say that x approaches c. When we say x approaches infinity, a positive infinity, x approaches infinity going to the right without bound. If we say x is going to negative infinity, x is going to the left of the point and going in the negative direction without bound. In our first example, we're giving the function is equal to x minus 1 divided by x minus 3. We're going to complete the following statements. As x approaches a positive infinity, f of x is approaching 1. And we can see that on the graph. As x approaches a negative infinity, we're now over here, f of x still approaches 1. As x approaches 3 from the positive side, we're going from this direction to this way, up to 3 from the positive side, we notice that x is approaching infinity. As x approaches from the left to the right, we see that we're going to a negative infinity. Now I would like you to pause and see if you can do the following completing statements. Now that you're back, we can say as x approaches a negative infinity, right? So we're going in this direction. We notice that f of x is approaching 0. As x is approaching a 2 from the negative side, we're going from this way, we see that x is a negative infinity. As x is approaching 2 from this direction, we see that f of x is approaching infinity. And finally, as x is approaching a very large number, we see that x is approaching 0 again. Our second objective is to define vertical asymptotes. The line x equals c is a vertical asymptote of the graph of the function f if f of x approaches infinity or negative infinity as x approaches c from either side. So, x can approach from the positive side, it can also approach infinity, a positive infinity, or It can even, in fact, approach a positive infinity going from the left side. Additionally, as x approaches c from the positive side, right, we could still have f of x approaching a negative infinity, or as x approaches from the negative side of c, we can see that in fact f of x can approach a negative infinity. So how do we identify vertical asymptotes of a rational function? Let f of x equal p of x over q of x, where p of x and q of x have no common factors other than 1. To locate the vertical asymptote of f of x, determine the real numbers x where the denominator is 0, but the numerator is non-zero. Here are some examples. Identify the vertical asymptotes, and if any. So the first step is we're going to factor. So here we have f of x is equal to x minus 3 over x minus 5, x plus 1. Now the denominator part, we see that x cannot be 5 or x cannot be negative 1. These are our vertical asymptotes. Now, I would like you to try the next two examples. F of x is equal to x minus 3 divided by x squared minus 2x minus 3. Please pause and try. Our first step is to factor the denominator and then set the factors equal to 0. So f of x is equal to x minus 3 divided by x minus 3 times x plus 1. Now we don't cross out the x minus 3 and say, oh, we only have x plus 1. We still have the x minus 3 in the denominator. So x cannot equal 3 and x cannot equal minus 1. Here are our vertical asymptotes. In our last example, we see that we have a negative in front, but we have an x squared here. So even if we set up x squared is plus 25 is equal to 0, we get no number of x squared where we can cancel 25 to equal 0. In this case, we have no vertical asymptotes. So these are problems similar to the ones in the book. Identify the vertical asymptotes. So in problem number A, you should be able to find the vertical asymptote. We know immediately that x cannot equal negative 1. So in this particular case, not only does this give us the domain, but it also tells us where the vertical asymptote is, at negative 1. Next, in part B, again, for the denominator, we need a factor 2x squared minus x minus 10 is equal to 0. So here we have 2x, and the question is, we probably have a 2 here and a 5 here. And so we have a minus here, and we have an x plus 2 is equal to 0. So now we have x is not equal to 5 halves, and x is not equal to 2. These are our vertical asymptotes. In the last problem, we noticed that x to the fourth plus 1 is equal to 0. So in this case, x to the fourth is equal to a negative 1, and we end up with an imaginary number, obviously. And of course, this means that there are no vertical asymptotes. Our next objective is to define horizontal asymptotes. Let the line y equal d is a horizontal asymptote of the graph of the function f of x approaches d as x approaches infinity or negative infinity. And so again, we have the situation where we can have something that looks like this. In either case, going in either direction, we can have something that goes like this, or something that goes like this. We can also have something coming from going to the negative infinity, which we have already shown. So we can have situations going in this direction. So, identifying horizontal asymptotes of a rational function. Let f be a rational function defined by two polynomials divided by each other, where we have a degree of a polynomial n divided by a degree of polynomial m, where n is the degree of the numerator and m is the degree of the denominator. If n is greater than m, f has no horizontal asymptotes. If n is less than m, then y equals 0, the x-axis, is the horizontal asymptote of the function. If n equals m, then the line actually is where we have y is equal to an over bm, the coefficients of the highest degree of the polynomials, is the horizontal asymptote of the function. So in this case, we have the function of the following. F of x is equal to 3x divided by x squared minus 9. Now obviously we can find the vertical asymptotes because when we factor, we have 3x and we have x minus 3, x plus 3. So we know we're at 3. We have a vertical asymptote here and a vertical asymptote here. So the horizontal asymptote we can see right away. Why? Because the degree of the numerator is 1 and the degree of the denominator is 2. Since 1 is less than 2, the horizontal asymptote is the x-axis. So in example 6, we want to identify the horizontal asymptotes, if any. Again, we know we can factor 3x squared of the denominator, x minus 3, x plus 3, and we notice that in fact at 3 we have an asymptote there, and we should put them in dots, and there's the other one. Now we notice that the degree of the numerator and the denominator are the same. So that means that as x gets larger and larger and larger in either direction, either in the negative direction or it gets smaller and smaller and smaller in the negative direction, that we end up with a function 3 over 1 as x approaches infinity or as x approaches negative infinity. So now our horizontal asymptote is at 3. In example 7, again, we know that we have the asymptotes at 3 and minus 3, the vertical ones. So we'll put those in. But the horizontal one, we notice that we have an x cubed divided by an x squared. So if we did the long division, we would end up with something that looks like 3x ultimately, and this is approaching a line. So as x gets very, very big, f of x approaches 3x, the line, right? And here is that line. So you'll notice our graph kind of goes around the asymptotes, the slant asymptotes and the vertical asymptotes. Look at how that's so nice as x gets larger and as x approaches a negative infinity, again f of x approaches a negative 3x. So in skill practice 3, we want to find the horizontal asymptotes, if any, for any given function. So for problem set A, we see that f of x is equal to 7/4 as a horizontal asymptote. And the reason why is because we have the numerator and the denominator of the same degree. When we do that, we just divide the coefficients of the two polynomials, in this case 7/4. So this means that as x approaches infinity or x approach a negative infinity, our horizontal, the function f of x, starts to approach 7/4. In part B, we have the numerator is greater than the denominator. In this case, there is no horizontal. Asymptote. In the final one, we see that the numerator doesn't have an x term and the denominator has a second degree polynomial. In this case, as x approaches infinity or x approaches negative infinity, n of x approaches 0. So our horizontal asymptote is 0 in this case. So crossing the horizontal asymptotes. The graph of a rational function may not cross a vertical asymptote, but the graph may cross a horizontal asymptote. Determine if the function f of x equals 2x squared minus 4 divided by x squared minus 3x minus 4 crosses its horizontal asymptote. Well, what is the horizontal asymptote? In this particular case, the horizontal asymptote is 2. And the reason why is because both the numerator and the denominator have the same degree. And when I divide them out, I see that 2 over 1 is equal to f of x, as x approaches infinity or x approaches negative infinity. Right? So we found the horizontal asymptote. Now the question is, does it cross? Well, to find if it crosses, we just set 2 equal to the following: 2x squared minus 4 divided by x squared minus 3x minus 4. And we solve the equation. We get 2x squared minus 6x plus 8 minus 8, is equal to 2x squared minus 4. Well, what happens is we see that those cancel, and we get a negative 6x is equal to, when we bring the 8 over, a 4. X is equal to a negative 4/6 or negative 2/3, right? So it will cross at 2 at negative 4/6. So yes, it does cross at a horizontal asymptote. So again, in practice skill 4 in your book, given that g of x is equal to 3x squared plus 4x minus 3 divided by x squared plus 3, determine the horizontal asymptote in the point where the graph crosses the horizontal asymptote. So you may want to pause and see if you find the answer to this real quickly. So the horizontal asymptote is going to be at g of x is equal to 3, right? And we can see that because we notice that both the numerator and denominator have the same degree of polynomials. And so we just divide the coefficients of the highest degree. In this case, when we do that, we get 3. Now, to find out where the point is that it crosses the horizontal asymptote, we now just let 3 is equal to 3x squared plus 4x minus 3 divided by x squared plus 3. Now we multiply through by x squared plus 3. We get 3x squared plus 9 is equal to 3x squared plus 4x minus 3. The x squares cancel, and we're left with 12 is equal to 4x. X is equal to 3. So at 3, right, we cross the horizontal axis of 3 of this particular function. Our fourth objective is to identify slant asymptotes of a rational function. A rational function will have a slant asymptote if the degree of the numerator is exactly 1 greater than the degree of the denominator. To find the equation of a slant asymptote, divide the numerator of the function by the denominator. The quotient will be linear, and the slant asymptote will be of the form y is equal to the quotient. So to determine the slant asymptote, we just notice that when we divide this into this, we will get a linear function, right? So in this particular case, what do? X squared minus 9, 3x cubed, 3x cubed minus 27 x. Well, this is not going to be important. What is important is that when we divide this out, we will get a linear f of x starts to approach 3 of x as x gets to be very large, or, for that matter, very small. So here is our slant asymptote. So in skill practice 5, it says determine the asymptotes, right? Well, now we're determining all of the asymptotes. The vertical one is at x is equal to a minus 1, right? Because x cannot equal minus 1, right? And the horizontal is the following. We have 2x squared minus 9, and we divided out x plus 1. We get a 2x squared plus 2x, and all we care about in this particular case, we don't care about anything else. We see that this now is g of x is equal to 2x if x approaches a very large number, or x approaches a negative infinity. So in this case, we don't have any horizontal. No horizontal, right? We have what? We have a slant asymptote at g of x approaching to x. So essentially we're going to be graphing rational functions where p of x and q of x are polynomials with no common factors. The first thing we want to do is always determine, guess what, x and y intercepts. And then we want to find our asymptotes, both vertical asymptotes, and then we want to find horizontal asymptotes, and then we want to find slant asymptotes if we can find either or all three of those. Actually, we either find a horizontal or we find a slant asymptote. Then if there is symmetry involved, if we have an even function or an odd function, those are very easy to graph. And then periodically we'll need to pick points to fill in the blanks. So here's our first example. We have the following, x squared minus x is equal to 6 divided by x squared minus 5x minus 6. So I'm going to factor this. I'm going to say, oh, this is x minus 3x plus 2 on the top. On the bottom, we have x minus 6, x plus 1. So this means that x cannot equal 6 and x cannot equal minus 1. So there is our definite, both the asymptotes -1 and 6, and it looks like these are basically, let's see, 2, 4, 6, 8, so these are by 2's. So 6 is 1, 2, 3, so here's my vertical asymptote for this particular one, so I'm going to put this in that. And then 1 is, -1 is here, so I'll put in my vertical asymptotes. The other thing we want to do is find some points in just a second. Let's also look to see, since the numerator and the denominator are the same, we're going to have a horizontal asymptote at 1. Does everybody see why? The reason why is when we divide x squared by x squared of the coefficients are 1. So the horizontal asymptotes is f of x is equal to 1 as x approaches infinity or x approaches a negative infinity. Now we have three pieces of our graph. We have the graph over on this side. We have a graph in between the two vertical asymptotes, and then we have a graph on the left side of the -1 vertical asymptotes. Now, the way we would approach this is, can we see what happens to the function as it goes from a 6 to infinity? So in this case, it's always going to be positive. So in this case, the function is going to go in the red, looking like this. Now we're going to go to the other side and say, okay, what's going to happen to the function when it's negative? So even if it's negative on both sides, we see that x squared over x squared are very large numbers in comparison to the other numbers. But we're not really sure yet how this function looks like. So what we're going to do is we're going to look at x-intercepts, and the way we do that is 0 is equal to f of x, which is equal to x minus 3 times x plus 2. So there is a y-intercept at at 3 and minus 2. So there's an intercept right here. So because there's a point at negative 2, we notice the top part is 0. So nothing else matters because it crosses this. So that means that the only way this function can look like looks like this. Now there's another point, right? It's at 3. So this is 2, and there's a point right here on the x-axis. Now the question is, does it go above or does it go below? Or does it go both above and below the actual horizontal asymptote? Well, let's find the point of the horizontal asymptote. So 1 is equal to x minus x squared minus x minus 6 divided by x squared minus 5x minus 6. Now we get x squared minus 5x minus 6 is equal to x squared minus x minus 6. So guess what? The x squares cancel, and look at this, right? So now it says that we have minus 4x is equal to 0, or x is equal to 0. So when x is 0, right, we must be at 1, right? When x is 0, we must be at 1. Does that make sense? Hey, it does. A negative 6 over negative 6. So guess what this function does? This function goes like this, and that's how this function works. Here's another example. F of x is equal to x squared divided by x squared minus 4. I'd like you to try to graph this one yourself, and we'll be doing this in just a second. Okay, so now the first thing is we can find the horizontal asymptotes by just looking at the fact that the numerator and denominator degree of the polynomials are the same. which means that the horizontal asymptote is f of x approaches 2 as x approaches infinity or x approaches a negative infinity. So because the way this works is we're going to see that we have the horizontal asymptote along 2. Now, we want the vertical. Now here, we notice that this is 2x squared divided by x minus 2, x plus 2. So we have the vertical at here and here. So again, we have 3 pieces of our graph. So now we say, okay, let's look at the positive side. And we know that this graph appears to be going in this direction. We can pick out points, but we have a general feel for as x becomes very large, we get closer and closer to 2, and that makes sense, right? And as we get closer and closer to positive 2, we go to infinity. Now, we don't know what the other parts of the graph are, so we're going to do a little bit of work. Okay, so now we have some very interesting things going on here. We've done some of the rest of it. We did the x-intercept. The x-intercept is at 0, 0, right? And so the y-intercept is also at 0, 0. So we have a point here. And we also found out that when we substituted 2 in for f of x for a point on the horizontal asymptote, we notice we get nonsense. And so this means that this particular point shows that it doesn't cross over the horizontal asymptote. So the only way that this function shall go will probably be in this direction. We can check with other points, but that seems the way it is. Now we look at the negative side, and we say, okay, well, since we don't have any other x-intercepts that will go across, that means that the graph on the other side of the negative 2 probably does not cross the x-axis. And in fact, that's the case. And because it doesn't cross the x-axis, chances are very good that it can't cross the horizontal either. So this graph will go exactly like this. So there's our graph. Here we have example 12, x squared minus 8x plus 8. And we want to graph this thing. And we see we have an x squared and an x minus 3. So in this case, we're probably going to have a slant asymptote where we have to divide the x minus 3 into the numerator. Before we do that, however, we know we have at least one vertical asymptote, right? X cannot equal 3. So we're going to put that in. These come in 3s, so we're going to put in our vertical asymptote at 3. And so this breaks the graph into 2 pieces. And we can find an x, a y-intercept, right? The y-intercept is f at 0, which in this particular case, when we see that, we get a negative 8/3. So at 0, we have a negative 8/3, which makes it approximately almost a negative 3, but it's not quite. It's about a 3 2/3, or 2 2/3 negative. So we have a point here. And the question is, well, now how does the rest of this go? Well, we want the slant intercept, slant asymptotes. So what we're going to do is we're going to do the division. So we have finished the slant intercept, and we did it by long division, and so we get a 2x minus 2. So add a minus 2, which we know is the y-intercept. We have 3 there, so 2, 1, 2 is about right here, approximately. And then we go up 2 and over 1, which is about right here. So we can draw our slant line going in this direction. I believe we can do that. And so now we have a point at 2, and it's that 2, 0. If we put 2 in for x, we will get 0 because we see that is our x-intercept. So when we get at 2, we will be at 0. And so this particular line goes, actually it should go like this. And then our other graph should look like this. Actually, we'll do it in blue. So in blue, our graph should look like this. And if we do it over here, actually we should have one that looks like that. So it should touch at 2, and we're here. So the y-intercept is right here at a negative 3/2 somewhere, and I don't think this is correct. Actually, this point is incorrect. It should be at 3/2, which is about right here. So that's where our graph is, and this is where the graph actually goes, based on the slant intercepts and the x and y intercepts. So in this case, we're just going to use a transformation to graph 1 over x minus 3 minus 1. So if we graph just 1 over x minus 3, we notice that in this particular case, if we were at 3, right, and we do need to bring it over at 3, we have a vertical asymptote at 3, right? Now, in this particular case, as x gets to a very large number, we get closer to the x-axis. So that's our horizontal axis. But we notice that we're at minus 1. So when x gets very, very large, right, f of x approaches a negative 1. So our horizontal asymptote is at negative 1. We've moved down 1 from 0. So in this particular case, when x is, say for example, 4, right, we have 1 over 1 minus 1. So that's at the x-intercept. So this graph actually goes like this on this side, right? So now we'll look at the other side of the graph, and we'll just pick, for example, a negative 1, and we'll get a negative 1/4 minus 1, which is a negative 1 1/4. So a negative 1 1/4 is about right here. And so this function actually looks like this. Our final objective is to look at maybe a potential application problem. So in this case, Young's rule is a formula for calculating the approximate dosage for a child, given that the adult dosage, for an adult dosage of D milligrams, the child dosage is C of X, may be calculated in the following manner. X is the child's age in years between the domain of 2 and less than 13. So in this case it says, what is the horizontal asymptotes of the function? In other words, and what does it mean in the context of this problem? Well, the horizontal asymptotes in this function, as you can see, is D. And in this context, it means that the dosage can never go over what is prescribed for an adult. Part B is, what is the vertical asymptote of the function? Well, obviously it's at negative. X cannot be a negative 12. But in age terms, this doesn't make sense. There are no vertical asymptotes of the function in terms of a negative, even though age can't be a negative 12. We'll never have a negative 12-year-old in our database. So for an adult dosage of 50 milligrams, what is the approximate dosage for a 9-year-old child? Well, we just plug in the C of 50, right? And so D of 50 over, or actually in this particular case that's not it, it's C of X is equal to 50X over X plus 12, and for a 9-year-old this is 50 times 9 over 9 plus 12, right, which is 450 divided by 21, right? So for 50 milligrams, we have about 21.4 milligrams that's given to the child. So the way this works is this graph isn't meaningful. The graph really only applies to 2-year-olds, right? Because it said from 2 to 12. So we're in a very small range, right? And so we're probably about right here on the graph. This concludes our chapter 3.5 of rational functions. Please continue to work on problems of the day.